Now this topic here is all related to Newton's laws of motion. Now in the previous work we've looked at Newton's equations of motion, v squared equals to u squared plus 2as, v equals u plus at, and all the other ones we've looked at. Those are called the equations of motion. What we're going to look at now are the laws of motion. There's three principal laws that governs all movement on planet Earth. And what the problem with this topic is that unfortunately it will bring in some cases, the equations of motion. So you can't kind of leave last week's work where it is and just forget it. In some of the questions here, we'll find we'll be needing some of last week's work, the equations of motion, to help us solve some of the problems this week. And that's where some students start to have difficulty with it. Not only have they got to deal with the concepts and the laws of Newton here, which are not always easy to apply, and they need a sort of valid framework in which to apply them, but also will be using effectively prerequisite work as well. So that's how these be quite difficult problems. And I must say, when I was studying what you're studying, back in the day, I found Newton's laws of motion quite difficult initially to grapple with and to apply. So the first thing I want to define though with you is something Newton defined, and that's a concept of inertia. Now Newton said that all bodies, and when we're talking bodies here we don't mean just human bodies, we mean cars or aircraft or whatever, all bodies which are at rest or have motion, and that's constant velocity condition, possess what he termed inertia. And you've probably heard this term before, but we're going to define it in a mechanical context here. Now this is how he defined inertia. Inertia is defined as the resistance of a stationary or a moving body, and that's a moving body with constant velocity. So that's the resistance a stationary or moving body has to a change in motion. In other words, to take a stationary body and to increase its speed, for example, or take a moving body and decrease its speed, there's an internal resistance in the body to undertake this acceleration or deceleration, to change its motion. And that's another way of thinking of inertia. You can think of it as a kind of reluctance to the object being accelerated, increasing its speed, or being decelerated, reducing its speed. Okay, that's inbuilt inertia as Newton defined it. And this is one of the laws you look at in a moment. The laws we look at in a moment are based around this concept of inertia. So bodies with large inertia, they're difficult to set in motion, or if they are in motion, to stop. Okay, so bodies with small inertia, the opposite is true. Inertia is effectively dependent on the body's mass. So the bigger the mass, the bigger the inertia effect, and the more resistance to a change in motion. All right, so greater the mass, the greater the inertia, this resistance to wanting to change the motion. And Newton said that to overcome this inbuilt inertia of a body and to cause a change in motion, so that could be to start it from rest, or it might be to slow it down or bring it to rest, we have to apply a force. Okay, so you'll see in a moment we've got these laws of motion, and they relate to forces. And there are three laws of motion. One primarily we'll be concentrating most on, which is the second law, but there are three, and I'm going to define all three here. We will use the first law or mention the first law in some questions, but it's the second law we'll predominantly be reviewing in the notes we're going to look at. So let's look at the first law of motion. It is sometimes called, in some textbooks, they call it the law of inertia. And this is what Newton states, that a body will remain at rest or continue to move in a straight line with a constant speed unless it's acted upon by a resultant externally applied force. So in other words, you can think of it to set a body into motion or to change the direction of the motion, an external force, which could be a pulling force or a pushing force, has to be applied. Now, in terms of a mathematical expression, the first law is often expressed like this. And this little symbol here, you see this Greek symbol, it's sigma. This symbol here is actually capital sigma. In the Greek alphabet, we use lots of Greek symbols, as you know. That just means add up. We've seen that before, I think, in another contexts. Add up columns of figures and so on. This means add up all the forces acting on a body and equate them to zero. That's what the first law means in a mathematical sense. We'll be applying that in some of the questions. Okay, so the first law states that if we summate all the forces, we add up all the forces acting on a body, they must equal to 0. Okay, so as an illustration of that, when I was in the aircraft industry, we often used to consider things called balance out on aircrafts. This is a sort of fairly simplified analysis here, but it shows the principle of a balance on an aircraft that's in what's called steady level flight. In other words, this is when the captain says we're now cruising at 38,000 feet and you can take your seatbelts off and you can, watching your videos or whatever. That is a condition that relates to Newton's first law. In other words, if you look at the forces acting on the body, if we consider the horizontal forces here, then the thrust from the engines, labelled it as T here, so engines are applying a thrust pushing the aircraft forward, is balanced by the drag force around the aircraft due to the aerodynamic friction effects and so on. So that's what's called a horizontal balance. If I add up all the horizontal forces, I would basically get, in this case, the thrust minus the drag is equal to 0. That's the expression for what's called the horizontal balance. And I'm assuming in this case that the positive direction is in this sense. One of the things we need to be careful of with what we're going to consider in the coming examples is that we are dealing with forces. Okay, and forces, as you know, they have a magnitude and they have a direction. So we always have to state a direction that's positive in the calculations we're going to look at. So my positive direction I'm showing here is from right to left. So in this case, the thrust is a positive force because it's going from right to left, and the drag is a negative force because it's going from left to right. So when I add those two forces up, I get 0. And that's what we would expect for a steady level flight in the horizontal direction. If you consider the vertical balance, consider the weight of the aircraft. Obviously, the weight of the aircraft always acts down. So there's the weight of the aircraft, that's acting down. Now, in steady level flight, that's balanced by what's called the lift force on the wings. Okay, so they're equal and opposite to each other, and they balance each other. So looking at the balance in the vertical sense here, if I say now upwards is positive, I need to give it a direction, a positive sense. Then to my balance on my equation, looking at upwards forces, I would have the lift force, they've called it L, going upwards. I would have the weight force coming downwards, that's a negative, and that equals to 0. So those are the horizontal and vertical balances in steady level flight, which is Newton's first law. Okay, and that's just for reference really. But basically what we're saying there is when we add up all the forces in either direction, the horizontal or the vertical, they must always equal to 0. So that's the first law. Let's look at the second law, which is the one we're going to predominantly concentrate on, although we will mention the first law in some cases. Newton's second law, this is how we define the second law. So when a body is acted upon by an external force, which causes the body to accelerate, the acceleration of the body is what's called proportional to the force applied in the direction of the force. Okay, now the second law can be written in mathematical terms as the summation of all the forces, but this time not equal to 0, equal to mass times acceleration. And that's that inertia thing that Newton commented on, that all bodies have this resistance to motion called inertia, and he defined it in terms of ma, mass times acceleration. So what they're saying there, for a constant mass, the greater the force you apply to the object, the greater the acceleration. So the force is proportional to the acceleration. So that proportional if the mass remains constant. Okay, and we're going to use that quite a lot in the work we're going to do. Force equals mass times acceleration. Again, I call it summation of all the forces because there's often more than one force applied to the body. So I'm adding up my forces. But again, we need to be very careful here. We are dealing with forces. So in the SI system, we need to use the newtons of force, not the kilogram. So make sure in all our calculations our forces are in newtons. And because forces and accelerations are vector quantities, we have to account for their direction. And that's very important. Okay, so it all sounds quite heavy, this, but I'm going to hopefully show you a little framework where we're going to apply these equations in a very structured manner when we get to the questions. Let's just do a very simple calculation. Hopefully you've done this kind of thing before in your previous studies, but I just want to take you through a very, very simple little exercise here, just applying the second law for the information given and just showing the units you need to be careful of. In this particular question, I encourage you to take this down. We have a car and it has a mass of 1 ton, so we're going to be very careful with that information straight away. We're told it is going to be accelerated at a rate of 2 meters per second squared, and we've got to calculate the accelerating force. So we've got to find the F in this case, okay? Now with all these exercises, I would strongly encourage you to draw little diagrams. It might be very crude diagrams, but I would draw very small diagrams of all the scenarios we're going to be given. So I'm going to try and draw as best I can a little car, a wacky races kind of car here. Okay, very crude diagram. You can just put a block if you want to. It doesn't have to look like a car even. In this case, we've got a force applied. I'm going to call that P for my applied force, my push if you like, that way. The force applied is what we're trying to find. Okay, now we're given a mass in the question. We need to be very careful with the mass. The mass is given in terms of a ton, and hopefully you can convert tons to kilograms. So that mass in this particular case is 1,000 kilograms. You mustn't use tons in the calculation. You must use kilograms. So 1,000 kilograms there. And the acceleration that it said we achieve here is got to be 2 meters per second squared. Again, notice the units of acceleration, it's meters per second squared. Velocities are in meters per second, accelerations in meters per second squared. So make sure you get your units correct. So we want to find the force, so I'm going to apply the second law here. Why the second law? Because it's accelerating, okay? If we've got an acceleration in the system, or as a given acceleration, or asked to find an acceleration, we're going to be applying the second law. So I'm going to apply Newton's second law. So I'm going to write that down here. So always in these questions, make sure you put down the formula. So the summation of all the forces. I think in your formula sheet it just says F equals ma, but I normally put the summation of, because often there can be more than one force. There is only one force in this case. Summation of the force equals the mass times acceleration. The force in this case is going to be P, and the mass in this case is 1,000. The acceleration is given is 2, so simply work that out as 2,000 newtons. So we would need to apply a force of 2,000 newtons to this little car here, given its mass, to accelerate it at 2 meters per second squared. If we want to accelerate it at 4 meters per second squared, then we'd have to apply 4,000 newtons. All right? So that's the simplest type of equation we can get. We're going to get slightly more complicated equations to deal with than that, but that's the basic principle of applying the second law to these problems, looking at the forces, looking at accelerations that are achieved and so on. And you'll find that the questions will play tunes on the equations. I'll show you that as we go through the examples. And I'm going to mention the third law here. This is really something that's implicit in the other laws as far as we're concerned. So we're not directly going to consider the third law as such. I will mention it where it occurs, but it seems like implicit in the other two as far as we're concerned. I'm just going to mention it for your reference. This is Newton's third law of motion, which says simply that to every force there is an equal and opposite reaction force. Okay, so the forces which two bodies exert on one another are always equal in opposite directions. And just kind of showing you here that in this situation we've got a person as a weight force of 850 newtons and stood on the floor. There must be an equal and opposite force from the floor on the man of 850. So this must also be a reaction force here of 850 newtons if he's going to stay stationary on the floor. If he falls through the floor, then obviously it wasn't equal and opposite. There wasn't a reaction force that could withstand his weight force. But so you can think of this top force is the force from the man on the floor, and this lower force is from the floor on the man. That's the effect of the third law. So we'll mention that where we need to in the calculations we're going to look at. So this is called application of Newton's second law here. And because it's deal with forces, I'm going to look in first of all the horizontal direction, and later I'll look at the vertical direction. okay, because there's a slight difference in the applying Newton's second law in these two directions. Some of you, I'm sure, from previous work will have looked at inclined plane motion. Imagine an aircraft taking off on a runway, that's considered to be inclined motion. But I'm not going to look at that in this particular point in time. I'm just going to keep things as basic as we can, so just horizontal motion or pure vertical motion, okay? So in this little sketch here, we've got a car basically, and it's shown as being accelerated. There's an acceleration in the system shown here. We've got an externally applied force to the car, and that's shown as P in the diagram. That's the externally applied force. Now there is also in this case what's shown as a reaction force or a attractive force here. I prefer to call this as attractive force, R, and that's like a resisting force, and that's due to, say, the friction of the bearings at the wheels. That could be aerodynamic friction opposing the motion, could be the tire friction for the rubber on the road surface. There's all sorts of reasons why we might have this attractive resisting force, but in some questions you will find that they will mention attractive resisting force, which is generated by some kind of friction effects. It might be headwind, as it says there. So I've got an acceleration, which is from left to right. I've got my force applied from left to right, but I've got this reacting force going from right to left. And what you're seeing on the right-hand side is what's known as a free body diagram, to use sort of the jargon. This is a free body diagram, and they're very important bits of kit with this work. We always should sketch a free body diagram. They can be very crude, might be just a block for the car, that's all we need. But on the free body diagram, all the forces are added, and that's the key. All the forces should be added to the free body diagram. And then from there we can build up our little mathematical model. Notice they've also given the positive sense direction here. You must always have a positive sense direction because you're dealing with forces here. So they're saying left to right in this case is the positive direction for all forces. So if I consider the applying Newton's second law now to this particular problem, so this is application of Newton's second law. Why the second law? Because it's accelerating. I'm applying it in the horizontal direction, and I'm using the positive notation shown in the sketch up here on my free body diagram. So applying the second law, it's summation of all the forces must equal to mass times acceleration. That's the equation. That is it. That's what we were given to apply. Not actually in that format. Back in Newton's days, it's actually a different format, but that's how we would apply it today if you look in your textbook. So all I need to do now is think to myself, on the left-hand side of the equation, what are the forces acting on the body? So looking at my free body diagram I have here, I can say I've got an externally applied force, P. That's a force that's acting on the body. And the direction of P is in the positive sense for my free body. So it's going from left to right, which is my positive direction. So I put that as a positive P in my little equation. What other forces do I have? Well, I have the reaction force, the R force, what I call the attractive force, if you want to think of it as that. The friction force, I prefer to think of it as. And that's going actually from right to left, looking at the sense of the arrow for the attractive force. So in my little equation, I would put that as negative R, because it's going the opposite sense. Have I got any other forces applied to my body? Now, some students think, oh, we've got the acceleration, but acceleration is not a force, okay? It's a sort of resultant of the forces that are applied here. It's not a force, so you don't consider the acceleration on the left-hand side of the equation. It's actually on the right-hand side over here, as you can see. So on the left-hand side, I've only got my forces. In this particular case, I've only got P and I've only got R. P positive and R negative. On the right-hand side, I put the inertia effect, the mass times acceleration, onto the right-hand side of my equation. Okay, so that's really how we're going to apply Newton's second law in all the questions, as you see in that little diagram there, in that little model. That's the way we're going to apply it all the time. We're going to consider all the forces on our free body diagram, and we're going to equate those forces to mass times acceleration. That's it. Okay, now if the question wanted us to find the applied force P, then I simply would rearrange the equation by adding R to both sides of the equation, so P is equal to MA plus the R. Simply transpose the equation. And if I had a situation where there were no tractive forces, sometimes they can be neglected because they're so small, they don't really affect the analysis, then of course the R would disappear and I'm back to the P is equal to MA, like in the previous exercise. In most cases, I think you will get these tractive resisting forces, so you'll need to consider them. Okay, but if they're not there, not mentioned, then you don't account for them, and it makes the analysis slightly simpler. So that's applying Newton's second law in the horizontal sense, and we're going to show examples of that in a moment. I want to though consider the situation where we're going to apply Newton's laws now in the vertical sense, and it's slightly more complicated in the vertical sense. If you think of the person in the lift here, and this is again my free body diagram. I always draw these free body diagrams. This is my free body diagram showing you all the forces acting on the lift here. I've got force P is an upward force. That could be, say, from the rope in the cable that's pulling the lift upwards. I've got a resisting force to the motion, and that could be to friction effects of the pulley systems, of the cables in the sheaths, or so on. There's all sorts of reasons why I might get that resistance. Notice that's going in the opposite direction to the motion. The motion is up, so the resisting force goes downwards. And in this particular case, I've also got the weight force. Because we're now looking in the vertical sense, we're applying our balance, if you like. We're applying Newton's second law in the vertical sense. Well, the weight force has to come into the equation. It didn't come into the equation in the horizontal balance. We have weight force there. And obviously, weight is still part of this system. There is a weight force acting down in this sense here. But it doesn't come into the horizontal balance because it's at right angles to the P and the R. So it doesn't come into the equation. So we can ignore the weight force in the horizontal balance, but we cannot ignore it in the vertical balance. We have to consider it. And again, in this case, I've got my acceleration going upwards. I usually consider my positive directions for the forces in the direction of the acceleration. That's what I usually do. It just makes the numerical work a little bit easier if you think of that. So if my acceleration's up, I make my positive direction up. If the acceleration's been down, I'd make my positive down. It's just the way I structure my calculations. You don't have to do that, but I find it just slightly easier for students if they kind of remember that. Now again, just applying this principle of the summation of all the forces equals to mass times acceleration. That's the equation we're using for the second law. So on the left-hand side, I'll now add up all my forces. And looking at my free body diagram, I've got P, which is positive, because it's going in a positive sense, it's going upwards, so P is positive, but I'm subtracting from that my weight force, because that's going downwards, so that's in a negative sense, and I'm subtracting also the resisting force, the frictional force, because that's also going downwards. So in this case, I have 3 forces on the left-hand side, and that equates to mass times acceleration on the right-hand side. Again, if they're asking me to find the force, I would simply rearrange the equation by adding the weight force to both sides, adding the friction force, resisting force to both sides of the equation. So P is equal to MA plus W plus R. Okay, so that's the kind of things we're going to do. It's quite complicated stuff, but I'm going to try and show you as best I can in this sort of framework that we're going to use over and over again. So what you're seeing on those 2 slides, the previous slide for the horizontal balance and balance here on this slide, we're just going to apply that every time to the questions, and hopefully you'll start to see that there is some structure here to what we're doing. So let's look at exercise 3, and let's take the information from the question. And obviously each time we've got scenarios. Our body, if you like, will be different. Our body might be a car, it might be an aircraft in this case, it might be a train, it could be a stagecoach, it could be a human being, the bodies will provide different contexts, but that doesn't really affect what we're doing. So exercise 3 I'm looking at here. Now we've got a 5.3 ton aircraft, travels across a horizontal runway with an acceleration, called the A there, of 1.5 meters per second squared. We've got to draw the free body diagram. I'll draw them anyway, of the aircraft, and we've got to determine the tractive resistance. So in this particular case, we're trying to find the tractive resistance, R, if we're given the applied thrust, and the thrust is like the force applied, to think of it as the P force applied, of 8.4 kilonewtons. Now, which of Newton's laws of motion do we need here? Obviously, this aircraft is moving, so the laws of motion are applicable, but do we need 1, 2, or 3? Well, in this case, we're going to need law 2, because law 2 relates to an acceleration, and we're told that the aircraft is accelerating. It's 1.5 meters per second squared. So we'll be applying the second law in this particular case, all right? First thing I'm going to do, though, is draw my free body diagram. So I'm going to try and draw an aircraft here as best I can. My aircraft always look like flying sharks, unfortunately. You can just draw a rectangular block if you want to, like a flying dolphin, doesn't it, that one? Because I worked in the aircraft industry for 12 years, I should be able to draw better aircraft than this. But anyway, there's my aircraft on the runway, level runway, don't level there, but it's a level runway. We're given in the questions information. We've got the mass of the aircraft. They say a 5.3 ton aircraft. Don't forget that's mass to us, so I'm going to write that down on my diagram. So the mass is equal to, I'm going to convert it straight into kilograms, so 5.3 tons, I'm sure you're all okay. That's 5,300 kilograms. The acceleration, we're told in the question, A is 1.5 meters per second squared. Let's go from left to right as I've drawn it here. And we're also given the applied thrust. Now that's the force applied from the engine. I'm going to draw it at the back of the aircraft here. That's the force applied to the aircraft. That thrust is backwards. In Newton's third law, action and reaction, means that the force applied to the aircraft is forward. So that's why we get the forward motion here. And that's 8,400 newtons. So I'm going to remove the prefix so I don't forget it. We've got to find the resisting force. Now the resisting force will go in the opposite sense to the motion here. So I'm just going to show an arrow over here. And this will be, I'm going to call it R for resisting force if you like, call it what you want to, but call it R for the resisting force. So there's my little free body diagram, all right? So, and I always encourage you to draw free body diagrams. You often get a mark for the free body diagram. Okay, I'm going to apply Newton's second law here. Why second? Because it's accelerating. So apply Newton's second law. And that would be a summation of all the forces are equal to mass times acceleration. That's what we're given. So on the left-hand side, I'm going to have all my forces. I'm just going to equate that to the mass times acceleration. Now, I need a positive sense for my diagram, what we call positive sign convention. I'm going to have my positive direction, the direction of the acceleration. So I'm going to say any force going in this direction, any force or acceleration in this direction, will be positive. So we must always have a sign convention. It doesn't matter if you choose the other way round, it can go the other way round. The complication if you make the sign convention in the opposite sense to what I've shown is that the acceleration then becomes negative, and some students forget to write that as negative in the equation. So if you always take the positive sense for your free body diagram in the direction of the acceleration, hopefully you won't make that mistake. So what I'm going to do now is add up the forces on the left-hand side of the equation. What are the forces applied here? They're my big red arrows are basically on my diagram. And I'm going to get P minus the R is equal to MA. And I said what these questions do is they play tunes on this kind of equation. This time they want us to find the R. I'm going to show you the transposition here on this particular exercise. How do you rearrange for the R? Now, the way I would approach this transposition, I need R to be positive, is my first step here, I would add R to both sides of the equation. So P is equal to MA, add my R, make my R positive, and I would subtract from both sides of the equation the MA. So P minus MA is equal to R. I think sometimes it's easier to see the equation transposed when it's algebraically formed. I'll just turn the equation around, of course, because I want the R on the left-hand side. Okay, so just transpose the equation there. The students struggle sometimes with that transposition because the negative is on the R. Sometimes they will say to me to take away the P, which you can do, and then they forget that the R is negative. Don't forget what the symbol in front of a number or a algebraic symbol is with it. So that is a negative R. So some students get confused if they subtract the P, they then write R is equal to, and that's wrong, it's still negative R. By adding the R to both sides, you don't kind of get that problem. So that's my preferred transposition. What I'm going to do now is put the numbers into the equation. Because in my calculations, my R is equal to 450 newtons. So that's the resisting force to the motion. That's the force that has to be overcome. in this particular situation. So again, all I've tried to do here is draw my free body, put the information on the free body, apply my sign convention, and then apply, in this case, Newton's second law because it's got acceleration, and then rearrange my equation appropriately. I'm going to try and do that principle in every question as best I can. So that was a horizontal balance, exercise 3. Exercise 4 is a vertical balance. And we've got 3 scenarios here that we're designing the lift, in this case, with. So let's go through what we're asked to do in this particular question. So we've got a person in a lift having a mass of 80 kilograms. We've got to sketch the free body diagram, which we're going to do anyway, of this person. And we're going to calculate the reaction between his feet and the lift cage floor. In other words, the force from the lift floor onto the man. And we've got 3 scenarios here. If you were designing a lift for real, you would probably have several different scenarios. You have an upwards motion, downwards motion, you might have an emergency stop situation, this kind of thing. So they're given us 3 scenarios here. The first one, A, we've got to find the force on the lift floor when the lift cage is actually at a standstill. In the second part of the question, we've got to find the force when the lift cage is accelerating upwards at 1 meter per second squared. And then finally, we've got to find in part C, they've called it there, that when the lift cage is accelerating downwards at 1 meter per second squared. So 3 different scenarios, we've got to work out the force on the floor. So I'm going to draw 3 separate free body diagrams for this particular situation. Okay, and I encourage you to do the same. So let's consider part A, and that's where the lift is stationary. Okay, let's do my little free body. I'm going to draw a picture of a stick person, and I'm going to show the person stood on the floor. This is the lift floor. So this will be my free body diagram I'm looking at here, and the free body diagram, all it is, or all the forces that are applied to the body shown on the diagram. That's all the free body diagram is. It sounds very grand, but that's all it's trying to do is capture all the forces. So let's think of what the forces are in this particular case. Well, the man or the person here is stood in this position, so the gravitational field on Earth will have a weight force. So I'm going to draw my weight force. In a vertical sense, we must have a weight force. A weight force acting down here. So at the moment it looks like he's plummeting to the centre of the Earth based on that particular force, but we know he's stationary, he's at standstill in the lift, so there must be, from Newton's third law, an equal and opposite force applied to him. And I'm going to call this equal and opposite force symbol P. So that's an example of Newton's third law in action, where we've got the applied force W from the man on the floor, and we've got the equal and opposite reaction from the floor and the man, labelled as P now. So that's the only forces to consider in this particular case because the lift is stationary and it stands still. So now we have our free body diagram, and I've put a positive notation of upwards here, that's my decision. And I've also added the man's mass of 80 kilograms that's given in the question. So what law of Newton do we need to apply here? Well, it's going to be the first law, because we've got a body that's stationary. So writing the first law in terms of our mathematical equation, we have summation of all the forces applied to the body must equal to 0. So from the free body diagram, in line with the sign convention, that means we've got the force P acting upwards, so it's positive P in our equation, and the force W acting downwards, so that's negative W in our equation. They must equal 0 for equilibrium. On the next line, I simply rearrange the equation by adding W to both sides of the equation, so the reaction on the floor P must equal to the weight force acting down, which we can deduce by inspection from the free body diagram itself. All I do now is calculate the weight force using the mass given in the question of 80 kilograms and multiplying that by the gravitational acceleration, G, which we assume to be 9.81 meters per second squared. So force P, the reaction from the floor on the man, is 785 newtons. In other words, that's equal to the weight of the man. Okay, exercise 4 part B. We've now got a scenario when the lift cage is accelerating upwards at 1 meter per second squared. So again, I'm going to draw my free body diagram of the situation. So here's my free body diagram. Again, the mass of the person is 80 kilograms. We've still got my weight force acting down and my reaction force acting up, but this time we've got the acceleration in the system, which is upwards of 1 meter per second squared. So I'm going to say that positive in this case is upwards because that's the direction of the acceleration. So applying Newton's second law, summation of all the forces is equal to mass times acceleration. Looking at the forces on my free body diagram, upwards I've got P, so it's P minus, downwards I've got W, and that's equal to the mass times acceleration. Rearranging the equation, because we're trying to find P, the force from the floor on the person, I will get MA plus W. We know all the values in this case, so P is equal to the mass, 80, multiplied by the acceleration, which is 1 meter per second squared, and we add to that the weight. We calculated that on the previous slide. That was 785 newtons. So therefore, evaluating the force required from the floor onto the person in this case to accelerate at 1 meter per second upwards is 865 newtons. Why don't you check that solution? So exercise 4, this is now part C. We've got to consider the situation when a lift cage now is accelerating downwards at 1 meter per second squared. So we've got to find the force between the floor and the man's feet. Again, as always, going to draw the free body diagram. So it's just shorthand notation for positives, what I'm using there. Positive sense is downwards here. And that's because the acceleration is down in this case. You can take the positive sense upward, you can do that, but you'd have to account for the acceleration being negative if you do that. And again, I'm going to apply my Newton's second law. So summation of all the forces must equal to MA. But I'm applying it in this vertical sense with the acceleration down. So again, all I do is look for the forces, the red arrows on the diagram, and I just write them on the left-hand side in the sense of my sign convention. Now in this case, positive is going down, so that would make W the positive force on the left-hand side, and I would subtract from that P, the upward force, and again it equals to MA. I've got to rearrange the equation for P. We've done this kind of thing before, so I will add to both sides of the equation P. So first step, W is equal to MA plus my P, and then I will subtract MA from both sides of the equation, so W minus MA is equal to P, and we just always turn the equation around. Okay, put in my values now. So P is equal to the W, we have that from the previous slide, 785 newtons is a W, minus the mass hasn't changed. The acceleration is still 1 meter per second, but it's downwards, but that's positive in this particular case because I've shown my positives notation downwards. Work out P now, the force required to produce this scenario, and I get 705 newtons in this particular case. So less than in scenario B, because of course this lift naturally wants to fall down under gravitational acceleration. So in this case, it wants to fall down at 9.81 meters per second squared. If we had no reaction from the floor, and that's what would happen to the person in the lift. It would literally fall down at 9.81 meters per second squared acceleration. But we're restraining that because obviously if we design in a lift, we don't want them to experience such drastic acceleration. So we're kind of slowing the acceleration down to 1 meter per second squared. So we need less force in this case than we need in the previous force when we're trying to accelerate the lift upwards. Okay, but those are scenarios there looking in the vertical sense. We started off with the stationary case, that was the first law situation, and then we've looked at 2 scenarios using the second law. I'm going to look at exercise 5 with you in your notes. And predominantly the first part is the main thing I'm looking at. There is a part B and C here, which just brings in some other terms that we need to be aware of. But the main bulk of the question here is all about the first part A, which is the Newton's laws of motion. But read the question, see if we can extract the information from the question, see where we go from here. So exercise 5, we've got a load of mass 1 ton, and it's hoisted vertically by means of a light rope running over a pulley. And it's accelerated from 0.2 meters per second to 0.5 metres per second. So those are two velocities. I can tell by the units there, they're velocities. It says it travels through a distance of 750 millimetres. So this change in velocity from 0.2 metres per second to 0.5 metres per second occurs in 750 millimetres. There's also, it's going to complicate our situation still further, I notice, there's also a resistance to motion of 150 newtons. So quite a bit of information here. And we've got to sketch a free body diagram of the load, find what's the pulling force in the rope. Notice in the question it says light rope, by the way, in the top of the board there. That's code for saying ignore the inertia effect of the rope. If you had a very substantially thick wire rope, for example, and that was moving, then that might itself have inertia effects and have resistance to motion, and that would then complicate the analysis, because not only the load itself you're considering, but it would also be this very, very thick, chunky cable. But in this case, ignore the effect of the rope, its negligible effect on the overall motion. So that's why they say light rope in there. Now, I've got a lot of information here I want to take out the question, so let's try and construct a diagram as best we can of this information. Lots of things to consider here. So we've got a load, that's some kind of object, and that's got a mass of 1 ton. So straight away, I need to write that in terms of kilograms. So M is equal to 1,000 kilograms, the load we've got. And connected to this load is obviously a cable, because it's being hoisted vertically. So I've got some kind of cable connected here. This is sort of going upwards. It's actually going round a pulley, I think, is what they're trying to show. So it goes round a pulley here, and then the rope comes off like that. So it's just kind of a pulley. That looks like the scenario that we're given here. We're not really bothered about the pulley, but that's what they're suggesting here. What else do we know? We know that the load is accelerated from 0.2 metres per second to 0.5 metres per second. Now, I'm going to use my linear velocity notation here. So the initial velocity, I'm going to show upwards here. I'm going to call that U, initial velocity, that's a symbol we normally use. That's 0.2 metres per second. And some distance later, remember the distance in this case, we've got the final velocity given in the question. That's 0.5 metres per second. I've got an S there. 0.75, and that's metres. Okay, that's a distance over which the acceleration seems to be occurring. There's also a resistance to motion here, so I need to account for these forces. I haven't put any forces on the diagram yet, let's put the forces on the diagram. Resistance to motion in this case, if the motion is going upwards, we're told that it's being hoisted upwards, so there's a resistance to motion, we'll call it R, shall we, and that's going downwards, and that's 150 newtons. So that's my resistance to motion. Now we've got a pull in the cable. We're trying to find what the P is, the P value. I'll show that there, P in the cable. Okay, that's going upwards. The resistance to that motion is going downwards. And don't forget, of course, because we've got this vertical motion we're looking at, we will also have a weight force acting down. So there's my free body diagram with the forces on it. So forces make the free body diagram here. Okay, so the P is the force in the cable. We're trying to find that. That's an unknown in this particular case. The R is the resistance to the motion. We're given a resistance of 150 newtons in this particular case, and that will go in the opposite direction to the applied force P, because that opposes the relative motion. And of course the weight force always acts vertically down, so that's what's shown on the diagram there. So there's the information from the question, as best I can see, that we need to use. I'm going to take my positive sense in this case in the upwards direction, because of course the acceleration is upwards. So A will be in purple here. So my acceleration is upwards. I can see that because of the change in velocity. So I will make my positive sense here upwards. So anything going in the upward sense, any forces, accelerations, I'm going to make that positive in this case. So there's my little sort of free body diagram. A free body actually only has the forces involved here. I'm showing velocities as well, but it's really forces that you show on a free body diagram. Okay, so what law of Newton's are we going to apply here? Second law here, because we are accelerating, all right? So step one, apply Newton's second law. So let's put down our second law. Summation of all the forces must equal to mass times acceleration. So on the left-hand side, all the forces on the diagram we now need to consider. And again, I use red for my forces here. Upwards is positive. In this case, all I'm going to do is write the forces in terms of the sign convention. So I can see P is a positive force. It's going upwards on my diagram. That's in the positive sense that I've defined. So P goes upwards. I've got the W coming downwards, I've got the R coming downwards, so they must be negative in my equation. That's equal to mass times acceleration, we're told. What do I know in this particular question? Let's try and think through what we know here. Well, obviously don't know the P because I'm trying to find the P. Do we know the weight force? Well, at the moment, the answer to that is no, but I can find the weight force because I've got the mass given to me, and weight force is mass times gravitational acceleration. So I know I've got the weight force implicitly given. I can find the weight force in a moment. Have I got the frictional force, resisting force? Yes, that's explicitly given. That's going to be the 150 newtons. Have I got the mass? Yes, the mass is given in the question, but I don't have the acceleration. So this is a problem now. I've got one equation, but two unknowns. In all the previous work we looked at, we generated an equation for Newton's second law, or the first law. We could always solve it because we had one unknown in one equation. But now we've got two unknowns. We've got the acceleration and the force we're trying to apply, the force in the cable. So we're stuck. We cannot solve one equation with two unknowns. It's not possible. So we're going to think, how can I find the acceleration? And this is where last week's work comes into play, because in the question we are given the initial and final velocities, and we're also given the distance travelled. Now, if you think of last week's equation and you go back to them, there's my last week's lecture was about the equations of motion, and these are the equations of motion in the bolded box there. So I need an equation that will allow me to find the acceleration when I'm given the initial and final velocities and I'm given the distance travelled. Now, if you look at the equations, the first four are all containing time. And we don't have the time in the particular question that we're given here. But the fifth equation, that list, is v squared equals to u squared plus 2as. I've got the initial velocity, it's 0.2 meters per second. I've got the final velocity, it's 0.5 meters per second. And I've got the distance travelled. So I'll be able to rearrange that equation to find the acceleration. So I'm going to use this equation of motion to help me find the acceleration, and then from the second law I can find the force. Okay, so in this particular question then, to find the acceleration I need to use the equation of motion. From v squared equals to u squared plus 2 multiplied by the a multiplied by the s. I'm going to rearrange the equation to find the a in this case. So to go to our transposition, I'm trying to find the a, so I want to remove the u squared, so I'm going to subtract u squared from both sides. So v squared minus u squared is equal to 2as, and don't forget that's 2 multiplied by a multiplied by s. So I want to find the a, so I'm going to simply divide by the 2s. So on the next line, space, keep on the same line if I can, I'll go along here. So turn the equation around, the acceleration is equal to, let you put the figures in. According to me, I get 0.14 meters per second squared for my acceleration. Now I can go back to the equation and I'll be able to find the p value. Find p now. So from the p minus w minus r is equal to ma, I can simply rearrange the equation, so p is equal to the ma added to w added to r. Just simply transpose the equation. I've got all the terms I want now. I've got the mass in the question, I've calculated the a, I can find the w, I've got the r in the question. Okay, evaluating my force in my cable, I get to be 10,100 newtons. So 10.1 kilonewtons if you want to write it in kilonewtons. Nothing wrong with 10,100 newtons there. Okay, so that's quite a lengthy question for part A. We haven't finished the question actually, but part A is done now. So we have to find, so we applied Newton's second law, found we couldn't solve the equation because two unknowns, and then found the acceleration from the equation of motion, and then go back and find the force P. And in part B, it wants us to find what's called the work done. Okay, the work done. Now, that's something we'll be looking at when we come to energy methods in a few weeks' time. And work done is simply force multiplied by distance travelled. So to find the work done by the force in the cable, we've simply multiplied the force in the cable by the distance travelled. So work done in this case, again, it's a bit confusing because sometimes we use W for work done and W for weight, so it's a bit confusing that, but work done is often used symbol W. That's simply the force in the cable, we've called that P, multiplied by the distance travelled, which we called S. So in this case, the P is 10,100, and that's multiplied by the distance travelled, which is 0.75 metres. According to my calculations here, that's 7,575 Newton meters. So 7,575. And you can call that Newton meters, or you can call it joules if you want to, because work is energy, and energy we often use joules. Part C wants us to consider the average power requirements. Mean power, average power, I use mean power. That's simply the force P in this case multiplied by the average velocity, which will be V plus U divided by 2. And that's just averaging the two velocities given. Okay, it goes back to statistics. How do we work out averages? We add numbers up and divide by the number of them, and that's just all we're doing there. We're just adding the two velocities up and then dividing by the number of them. Well, that's all that is. So 10,100. And that's multiplied by, and all we're going to do is add the velocities up and divide by 2. So 0.5 plus the 0.2, and that's all divided by 2. And according to my calculations, I get 3,535. I don't get power, you probably know already, is in terms of watts. Okay, so that's a very complicated question. That's as good as it gets at this level. You'll be pleased to hear that. I haven't seen anything more complicated than that. It's a very difficult question, but again, we try and take it through very carefully in our solutions. All right.